So it's my special honor and great pleasure to introduce the next speaker, Professor Edgerton from Princeton University. She will talk about positivity for a class of covariant operators.
So it's a great pleasure to visit and an honor to give a talk here. Okay. So today I will talk about some joint work with my colleague Jeffrey Case, who is also here. And we will talk about the positivity of a class of conformal covariant operator. So let me explain my title. So the class of conformal covariant operator I'm going to talk about is a class introduced by Grant, Jenny, Manson, and Sparling called GJMS operator. And that's introduced in 1985. So this is a class of operator with a conformal covariant property. What that means is when I look at the operator operating on a function phi, and then if I change the class of metric conformally, then this operator operating on this conformal factor to this power phi and multiply by this. So this is a class of operator, and GJMS said it exists with the leading symbol minus Laplace to the k's power when 2k is less than equal to the dimension. So the operator we have in mind is the well-known operator when k equal to 1, and that's the conformal Laplace operator, or the Yamabe operator. So it's just Laplace plus some multiple of scalar curvature. Notice that in this constant here, the multiple of the scalar curvature here, the constant is d minus 2. So when the dimension of the manifold is d equal to 2, we are back to the Laplace operator. So in other words, from this expression, this conformal Laplace operator, when d equal to 2, dimension equal to 2, you do not see the curvature. On the other hand, we do know that a proper replacement of the scalar curvature in two-dimensional manifold is Gaussian curvature. And this observation plays an important role in this property of this class of conformal covariant operators. So, and when d is greater than 2k, then the q operator associated with this p operator is defined by it multiplying on 1. So as I said, when d greater than 2, then q2 is just the scalar curvature, but when d equal to 2 is the Gaussian curvature. And when the dimension d equal to 2k, this class of curvature is called, usually just denoted by q2k is a Bronson's Q curvature. And this is, in our mind, in some sense, a replacement of Gaussian curvature when you restrict to the manifold on locally conformally flat manifold. So it has the property that when the manifold is locally conformally flat, then it's just the integration of the curvature is just the Euler characteristic. And in general, this is also a curvature of order d. That means you differentiate the metric d times, and the integration of that is a conformal invariant. That means when g equal to gw, changing conformal class, this is an integral invariant. And there has been lots of study of this class of operators, but today I will just talk about an extension of this operator to the fractional power, and that relates this class of differential operator to a class of pseudo-differential operator and defined on the manifold. So on the boundary of the manifold. So this is the operator introduced by Grant and Zosky, okay, fractional operator. And that's defined on 2n less than equal to n. So it also has this conformal covariant property. And when, say, for example, when gamma equal to 1, P2 is the conformal Laplace operator, and P1, that means in my notation, a first order operator is just the Neumann operator plus the mean curvature. So Q1 is the mean curvature. And say when dimension n equal to 1, P1 is just the Neumann operator. So we are going to, the problem we are studying is trying to decide when is this class operator a positive operator. So the problem is that the positivity is on the boundary P2 gamma f is positive for all function f. And you may ask, why are we interested in such a problem? Okay. And one of the reasons is certain condition like this, since this P2K all are linear operator in a sense, so the positivity leads to solutions. We want to know its eigenvalue. And so frequently, a criteria for positivity leads to the solution of a constant Q curvature operator in the same conformal class of method. But there is also other reason we are interested to study this positivity, and which I will mention hopefully at the end of the talk. And so when gamma equal to 1, and since this P2 operator is just the conformal Laplace operator, P2 is just Laplace plus the constant times scalar curvature, and this is a positive constant. So when the scalar curvature is positive, P2 of course is positive operator. And now let me mention that there is one result which actually is a very beautiful result and play a significant role in the development of our understanding of Q curvature. And that's a result by Matt Gursky, which he says that on 4 manifold, if it's a closed manifold, so this P4 operator on 4-dimensional manifold has the property that it is pointwisely conformal covariant. So it's on metric GW, which is in my notation is always E2WG. This conformal factor just take out. This is P4 of G. Okay. So in the 4-dimensional case, if we want to study when is the operator positive, we are seeking a condition which is conformally invariant. Okay. And Gursky pointed out this condition is given by the following 2 constants which are invariant. One is the Yamabe constant, one is the integration. So these 2 constants decides the positivity of the P4. So it's a very beautiful result because it's not clear from the expression of P4 that is the case. So, so it's not a pointwise curvature condition, but an integral Q curvature condition. So here I like to say that in D dimension, P4 starts with minus Laplace square and but plus some lower order, second order term, the coefficient of the second order operator involving Ricci curvature and scalar curvature. And then there is this D minus 4, Q4 there. And for the rest of the talk, we also try to remember Q4 in any dimension always take the form some constant Laplacian of the scalar curvature and then plus some constant scalar curvature square and minus some other constant of the Ricci square. And this constant depending on the dimension. So it's a 4th order in a sense. Scalar curvature, I think about it as 2nd order. Okay, so this is just some
Constants are not all positive.
Yes, because here I write it traceless recede, then it becomes, this AB are positive constant. So in this way, I should maybe write a C. So my ABC all are positive constant, then there is a cancellation. Okay. So for example, when it's Einstein, then this is just a constant. Okay. Q is a constant. Okay. And now, there is also a lot of recent work which further study this fourth order operator and to study its positivity. So let me mention a recent preprint of Gutsky and Marchiodi, and where they instead, in D dimension, when D is bigger than or equal to 4, they say that instead of, in this case, this operator is not pointwise covariant, conformal covariant. So the condition they put is if scalar curvature is positive, and if this Q4 is positive, then P4 is positive. Then this D is greater than or equal to 4. And in the same paper, they actually made a very in-depth study of this P4 operator in D dimension. And for example, they understand the Green's function, the positive mass result relate to this operator, and then it proves a strong maximum principle. A function P4U positive imply already U is greater than or equal to 0.
This is a global result? Local?
Yeah, it's a global result. Global result. Okay. And it turns out this P4 operator is also interesting in dimension D equal to 3. So you are talking about fourth order operator in 3 dimensions. It seems to be an overkill. But in that case, there are some other phenomena occur. For example, on the standard S3, it turns out this operator has one negative eigenvalue, this P4. Okay. So this scalar curvature positive and Q4 positive will not imply P4 is positive. It still sometimes has a negative eigenvalue, but on the other hand, in that time, one can see that the recent work of Han and Paul Yang shows that one understands the sign of its Green's function and the positivity, and also the strong maximum principle. Okay, so the result I want to talk about today is positivity of this fractional order operator. And I treat this operator as a boundary operator. And it's a boundary of conformal compact Einstein manifold. And so this operator is a pseudo-differential operator defined on the boundary, but its precise form depending on the extension inside. So there are 2 results I want to report today. The first result is we look at this P2 gamma operator. So this P2 gamma operator, the leading symbol is always Laplace to the gamma power, but there is some other term. So when gamma is between 1 and 2, and when dimension is bigger than or equal to 2, and then it turns out we need a constraint, and that constraint is we look at, this is on conformal compact Einstein manifold, so there is an Einstein metric G plus, which is Poincare Einstein, and we want its first eigenvalue greater than n squared minus gamma squared. Then in that case, if Q is positive, imply P is positive. Okay. And so that condition that this constraint on the first eigenvalue on this Laplace operator turns out to be natural in the sense that there is an early work of Jack Lee which says that if this G plus, after you compactify it, and if the boundary operator has positive scalar curvature, then the first eigenvalue of this interior operator, this Poincare metric, is greater than or equal to n squared over 4. So in a strong constraint, when the boundary has positive scalar curvature, then that condition is always satisfied for all gamma between 1 and 0. So that's the first theorem. But actually, I like to spend more time talk about second theorem because there's some other thing comes in, and which says that when gamma is between 1 and 2, we now look at an operator of order bigger than 2, between 2 and 4 now. So in that case, we also have a theorem which says that in that case, if the boundary curvature on the boundary is positive, and if this Q2, now it's nth, this Q2 defined on the boundary of Mn, so it's Q2 gamma positive, then it's positive. And this result holds for all n bigger than or equal to 4. And when n equal to 3, it turns out the result holds up to gamma between 1 and 3 over 2. And gamma equal to 3 over 2 turns out to be the most interesting case, because in that case, we are studying a third order operator defined on a manifold, which is 3 plus 1. So the constraint is a third order operator defined on the boundary, and then inside it's a fourth order. So it's the most natural pair. Okay. So we have these two rather technical theorems, but I like to try to explain some idea behind improving this result. Okay. And the key step in the proof, actually the only point of all this proof is on a conformal compact manifold, we have this conformal infinity. And on conformal infinity, the metric is decided up to conformal class. So when you fill it in, that there is a problem if you want to compactify the manifold and studying the compactified manifold, what is the conformal class, conformal metric you should choose? Okay, so the right choice of the conformal compactified manifold is the key of the proof. Okay. So we want to show there is a natural compactification process in all these problems.
So, going back to the statements you're making, though, are dependent upon the particular x. So, for example, you're saying something about the first eigenvalue of the Laplacian on this interior x. So
yes. Yeah, that is a pre-assumption. And then under that assumption, we can make a good choice of metric. Our choice depending on that assumption. We want, yeah, I will explain. Yeah, it will be clear. That's right. That's right. But the thing to keep in mind is if the boundary metric has positive scalar curvature, this condition always happens. Okay. Now, I will get back to the proof of the theorem, but let me say what are the main tools. Okay. The main tool in the flat setting is the work of Covariant and Silvestro. That is, we are going to study a boundary operator, and we want to think about the energy of this boundary operator has a Sobolov trace inequality. So we are seeking a suitable Sobolov trace inequality, and in the classical setting, that's explained by the result of Covariant and Silvestro in 2006. And what they did is, on Euclidean space, if a function f is on Rn, and then you look at the situation on Rn, and then coordinate y there. So this is x in Rn in the upper half space. And we all know that if we have some function which is a Laplace u equal to 0 and u equal to f, then in that case, the partial derivative of u with respect to y is Laplace to the 1/2 operating on f. So this is the Dirichlet-Neumann operator. So this function, du dy, is just Laplace 1/2 to the f. My Laplace, by the way, is d squared dx squared, so minus Laplace is the positive operator. So the result of Caffarelli and Silvestro says that this result is true when you put some weight. And that weight is if gamma is between 1 and 0, and A is equal to 1 minus 2 gamma, then if we have this divergence YA gradient U equal to 0, U equal to boundary on the F, then this Laplace gamma F is limit of y to the A du dy. Okay, the limiting is that thing. But actually, the extension theorem says more. So let me try to write down this equation on the blackboard. So on a flat setting, and later on we will see there's this G plus, which is equal to dy squared plus dx squared, and then y squared. Okay, so in this flat setting, in this statement, this G plus doesn't come in. But what we have is we have this equation, which is divergence y to the 8th power gradient u equal to 0 on upper half space.
You're saying that the Dirichlet-Neumann map is a fractional power of the Laplacian in all this?
Yes, for all A between gamma between 1 and 2, 1 and 0. Okay. So, and this is U restrict to the boundary is equal to F. So that's the PDE I'm looking at, and this A is 1 minus 2 gamma. Notice that this A sometimes is negative when gamma is bigger than 1/2. So in that case, but actually what their theorem says is a little bit more.
I'm confused. So you're saying that for any gamma, could you back up?
Yes.
I'm a little bit confused at how you change the problem so that you get Laplacian to the gamma out of this, what's ostensibly the same.
I'm saying that suppose U is a function defined on the upper half space and solving the PDE, then you can recapture, of course F should be in some suitable class. It can be recaptured from the behavior of the partial derivative of U to the Y and with respect of weight.
Oh, it's the A that's very, I was reading that as an index, I see. Right, so it's the crucial power of Y.
Yes.
Y?
Yeah. Okay. So when gamma equal to 1/2, A is 0, so that's the classical result.
So Laplacian is in line, the U is in line equation.
Oh, this, yeah, this Laplacian is, I'm sorry, it's this Laplacian, flat. I shouldn't write this. This is confusing. So this is the usual X and Y Laplacian.
It's the Euclidean.
Flat, Euclidean, upper half space. Upper half space Laplacian. I shouldn't write this, okay. Later on you will come in. But so this, everything is flat. In the flat setting, we have this extension, okay. And now, what they have actually pointed out is that this PDE, the solution of this PDE, actually tells you what is the energy of this P2 gamma operator. So that means that if you look at the energy of gradient U square and y to the 8th power on y bigger than 0, that's actually minus Laplace gamma FF on the boundary. Okay, and so they look at its energy identity, and then they play the variational problem, and then you get this boundary behavior. This boundary behavior is consequence of the energy identity. So that's Caffarelli's.
Here is always the Euclidean Laplacian, it's not.
Yeah. So I'm sorry, I shouldn't write this. So this is the flat setting. Rn plus 1 plus is dx dy. On Rn it's dx. Okay? So yeah. So this is x, this is y. So that's this flat setting. Everything is flat. Okay, and now this theorem has been many application to free boundary value problem and some study on the local minimum surface, but I will not mention those. Okay, and now what we want to say is, we want to say that this kind of extension is a special case of conformal compact Einstein manifold. Okay? And this boundary operator minus Laplace gamma f now is equal to limit y tend to 0, y to the 8th power du dy. This operator minus Laplace to the gamma power can be extended as the boundary operator of P2 gamma. That's what we are trying to say. Okay. And so for that, I need to define the notion. Okay. So the setting I'm thinking about is, now I'm consider this upper half space with the Poincare metric, dx squared plus dy. And then instead of studying equation on this Poincare metric, I now compactify it. And the way I compactify it is multiply it by distance function square, y squared g plus. And in this case, I get a flat metric. That's the flat metric. So what I'm trying to say is a PDE on some suitable PDE on this Poincare metric, you can write it in terms of this compactified metric and in this coordinate. That's what I'm trying to say now. Okay, so for that I recall a definition of conformal compact Einstein manifold. So that is, if there exists a distance function such that G plus itself is Poincare Einstein and it's non-compact, I multiply it by distance function square, it becomes compact.
Distance functions, defining function.
Yeah, defining function, yes, okay. So, and now this defining function is not unique. There are many defining functions. So once you have a defining function, you have many choice. Okay, you mean many choice. So that means once you have this R squared G plus is a compactified metric, you can restrict it to the boundary. You have a boundary metric. But that boundary metric varies if you multiply R by some other positive function. Okay? So the boundary metric is only decided up to conformal class. But in this setting, it turns out there is some special defining function, and that defining function is denoted by this y here. And this y satisfies, this is a typo. If we multiply y squared by g plus, and then gradient y is equal to 0, it is equal to 1 on the boundary cross a small neighborhood of the conformal infinity. Okay? But this existence is Cauchy-Kowalski theorem, so it's only for a very small neighborhood. So this is not a coordinate on the entire manifold, but on asymptotic infinity. Okay, so and based on this observation, we can write this G plus on near infinity as in this way, and where Gy has some expansion, and I denote Gy restrict to y equal to 0 equal to G0. So, but Gy in general is a power series expansion of G0 plus G2 y squared and so on. There's an asymptotic expansion.
So Gy doesn't have any dy's in it, but it's a function of y.
Yeah, Gy is, yeah, that's, okay. Gy, the only information you know at this moment is y equal to 0 is some boundary metric. Actually, given G0, you can solve some y, and which can be predetermined, and then you have something G2 metric and so on. But one problem in this field is this G0, G2 up to Gn is decided by G0, and there are other information not determined. Okay? So it's not completely determined by the boundary metric. Okay. Okay. And now let me try to say what is this GJMS fractional operator. So on the CCE setting, one begins by look at the Poisson equation. So on this x n plus 1, and then boundary x, and I have a Poincare metric, which is a CCE, can be compactified. One begin to look at a Poisson equation. So this is what I call Poisson equation. One look at this equation. And with Dirichlet data. Which is a function on the boundary. So what does that mean? That means the following thing. So if one look at this equation, one knows that there are two approximate solutions, and one of them turns out to be y to the s power, the other is y to the n minus s power. Okay? And so that means that you can begin to let me first say when is this equation solvable, and there is a work of Mazzero and Melrose. They say that not only on CCE setting, but on asymptotic hyperbolic manifold. This equation, the eigenpoint, there is an essential spectrum, and there is a point spectrum, and point spectrum is only finite many points in between 0 to n squared over 4. Okay. And so for real s greater than n over 2, except for finite many of lambda, this y to the n minus s and ys are asymptotic solution of this equation. So that means that you can, near infinity, using this coordinate, you can write this u as a function y to the n minus s power times some function. This is a function of x and y, and then plus y to the s times some other function. I don't know what's the symbol I use, h, there. Okay. And then the Dirichlet data means f restrict to the boundary is the given f. And in this case, we know we write u as the Poisson equation of f with Dirichlet data f. Okay. So we know this has an asymptotic extension and so on. But on the other hand, one is also interested in the information h there. Okay. So the information of h restrict to the boundary is defined to be the scattering metric of S operating on F. So that's the definition. Okay. So this scattering metric usually corresponds to Dirichlet data. I mean, this is Dirichlet data. Scattering almost like Neumann data, correspond to Neumann data, very, very roughly. Okay. So this is the scattering of metric. And this P2 gamma is defined to be, so here is the definition. We write S equal to n over 2 plus gamma, and this P2 gamma operator is defined to be this, sometimes there's a constant there, so n over 2 plus gamma. Okay? So this is at this special index, we denote this by this pseudo-differential operator P2 gamma. And we know it's a leading symbol, c to the gamma power, and this scattering metric happen to have simple pole at a point when gamma equal to integer, and that point one need to take its residue, and the residue becomes the GJMS operator. So that's this very, very rough definition of P2 gamma. And now let me say there are many examples besides this flat setting. In that case, the compactification is not really compact, but on the other hand, we can still treat the sphere as a boundary of the hyperbolic space and be a compactified CCE setting. In that case, the right choice of coordinate, if GH is the hyperbolic metric, we choose R to be this coordinate, then GH can be explained this way, and then this R squared GH is a compactified metric. Yeah. And of course, there are many, many other very sophisticated examples, and a large class of example is given by hyperbolic space quotient group and SN quotient group. And there is also an example like Schwarzschild space and so on.
You don't want it to be compact, you want something left at infinity.
Convex, co-compact, or Poisson group, or, I'm sorry. Yeah, so sometimes you want a manifold to be, locally conformally flat. So there's an example like that. Maybe I didn't write the right word. Okay. So there are many examples of such space. That's what I want to say. Okay. And now what we want to do is to rewrite this equation into that equation in CCE setting. Okay. And that is done in early work by Gonzalez and myself. We rewrite this equation. And the way we rewrite equation is now this U is of that setting. So what we do is we take rho, which is a distance function, another defining function, which behave like Y near infinity. But you need to define it on the whole space. And then you consider G equal to rho squared G plus. And then we look at this equation. We begin to consider this metric. And then the function one should look at is U is equal to rho to the S minus N times U. Because this function, U, restrict to the boundary, is the given function F. Okay. So when we look at this equation, and we know that these G plus and G are conformal to each other, so we can use, we can compute this G plus in terms of G, and then we rewrite our PDE. And so the rewriting PDE becomes the following thing. And this is divergence of rho to the eighth power gradient U in this G metric, and then plus some function which we can compute with respect to rho equal to this U equal to 0. So we just rewrite that equation. And then we look at these two equations. We know they are similar, and we can recapture boundary through this PDE. Okay, so that's the PDE. But in doing so, we wonder what that term is. And this term, depending on the defining function, and we know that when gamma equal to 1/2, then in this case, this E rho 0 happen to be scalar curvature of the metric. And the equation to the right power, there's a rho to the eighth power here, and is the conformal Laplace operator. Then the star is just the conformal Laplace operator. This is n over 2 plus 1/2 is the P2 operator. But for other value of gamma, this expression is quite complicated.
Is it always just acting by multiplication now? It's not a differential operator.
This expression has a gradient rho in it.
No, but I mean, it doesn't differentiate U, right? It's just being multiplied by U?
Yes. Yeah. This is a potential function.
So
Wait.
the point is that, so you're actually looking at an eigenfunction of the Laplacian, the interior Einstein metric.
Yes.
Thinking of it as a conformally weighted function.
Yes.
So when you restrict to the boundary, you give it this conformal weight, it's a power of the defining function.
That's correct. That's correct. Okay. So we begin to think, is there a reason that this expression is complicated? We also make one observation. And that observation is, if we make a right choice of rho, the defining function, then that term vanishes. Okay? So now let me say what is the right term. The right term is the following. We begin to look at the Poisson equation. But we now solve this equation to be the Dirichlet data equal to 1. Okay, the Poisson equation. And then the thing is, we don't know if we start with this Dirichlet data equal to 1, would the function v be positive? Okay. If the function is positive, then we know this function behave like y to the n minus s power near the boundary. So the correct choice is v to the 1 over n minus s power, if v is positive, because we want this to be nicely defined. If we can make such a choice, then the energy term equal to 0. So that's the observation. At this moment, it's a formal observation. And then, in this case, we begin to think, when is this eigenfunction with Dirichlet data 1 is always positive? And then, using this transform, you can solve this PDE and take inf of the solution, and using the uniqueness of the solution, you see that's equivalent to say that lambda 1 of this operator should be greater than Sn minus s. Okay? So in this case, Sn minus s is equal to n squared minus 4 over gamma. So it turns out that this v is positive if and only if we have that constraint. So in that case, the proof of theorem 1 becomes very easy. Okay? So let me first say one lemma. So theorem 1 is, I just want to say that if this v is positive, this Dirichlet Poisson equation on 1 is positive, then Q2 gamma positive imply P2 gamma positive. That's the theorem, theorem 1. And to prove this, we begin to look at the expansion. We choose this nice conformal factor, rho star, rho star. And then we look at its power series expansion. And because it comes from scattering operator, so we know its power is like this. And then we compute P2 gamma f. And we notice it's this boundary behavior of this function u and plus Q2 gamma f. So this is a lemma. So that means P2 gamma f is positive only if we can show this integration of this term on u is positive, because Q2 gamma is already positive. And then that is expanded by this PDE. Because in that case, this choice, this rho star vanishes. So the integration of the energy term is just the boundary term. Okay, so this divergence equal to 0, you integrate, multiply by u, and then you notice that this boundary term is recaptured by the energy term. So it's positive. Okay? And that's the proof of this theorem. Okay. And now I want to say that this look very simple-minded, and we try to see that what happens when gamma is bigger than 1. Okay? When gamma is bigger than 1, it turns out there is other phenomena happen. So this is the second theorem. Okay? Second theorem is we want to say that this is when this first theorem is for gamma is between 1 and 0, and second theorem is between 2 and 1. And then we want to say, under the condition, the boundary curvature, scalar curvature positive, Q2 gamma positive, then it's positive. That's what we want to say. And to do this, first, we look at the tool. Okay. So we look at this expression of this. We notice that in the original result of Caffarelli and Silvestro extension theorem, when they talk about the energy term, so in this previous theorem, when they talk about YA equal to gradient U square dx dy, they are very careful to say that this is equal to P2 gamma FF on the boundary. They are very careful to say that gamma should be between 1 and 0. The argument only works for gamma between 1 and 0. So we first ask, what are the suitable formula to replace such an energy term? Okay? And why is gamma between 1 and 0 necessary? So it turns out that there is an extension of this theorem for gamma bigger than 1, and to replace this energy by some renormalized energy, which I will explain, and this is done by Ray Young. And then the flat setting theorem, there is a statement on the flat setting, upper half space setting, and then in order to translate that result to general compactified Poincare-Einstein metric, we need to introduce other notion and think about the express this GJMS operator in general setting in terms of metric with magic, okay, with weights. Okay, so I will explain a little bit about that. And then, a third step is really to show that with this nice choice of the special defining function, there is not only a control of the Q curvature inside the manifold X, but also once you have boundary, the scalar curvature control, then the interior scalar curvature also has control. So that's the third step. Okay, so and then the fourth step is to apply this extension theorem, and then we go through some proofs similar to the argument like Gursky and Marchiodi theorem to establish the theorem. So that's the outline of the proof. So now let me extend, going through some of the steps a little bit. So the step one is the work of Ray Young to extend this Caffarelli and Silvestro's extension theorem. So for that, one used the following notation. So one used the notation that he used the notation multiply this equation by -a. And then notice that he used the notation Laplace A. So Laplace A operating on U. So Laplace A operating on U is just Laplace U plus A over Y du dy. Okay. And now the observation is, if you satisfy a second order equation, Laplace A equal to U equal to 0, on the boundary is equal to F, and if A is this index, 1 minus 2 gamma, then it satisfies Laplace B square, the bi-Laplace B square U equal to 0. And since this is a second order, this is a fourth order PDE, so the equation is there is for fourth order PDE, you want the solution to be unique, you need other boundary condition. And that boundary condition is yb du dy equal to 0 when y restrict to 0, and b become the index 3 minus 2 gamma. Okay? So the observation is this second order PDE is equivalent to the fourth order PDE, and with the additional constraint on the boundary, which is naturally satisfied by the solution of the second order PDE. Okay, so this is the first observation. And then what has that to do with this extension theorem? And then using this theorem, I'm sorry, there is a typo there. Okay, so when gamma is between 2 and 1, it turns out this boundary term P2 gamma FF on the boundary on Rn now in this case is the same as equal to Laplace bu square y to the b's power dx. So that means the suitable energy term is this Laplace to the square. Okay? So instead of this gradient u to the square, so there's a fourth order thing going on. And in this case, one can also recapture the boundary operator minus Laplace to the gamma power through this PDE. Okay. And so what he actually has pointed out is, say, for example, when A is equal to 1 minus 2 gamma, when gamma equal to 3 over 2, then A is equal to minus 2. Okay? And then when gamma is equal to 3 over 2, B is equal to 0. So the energy term we are talking about is this energy, Laplace u squared. And the original energy used by the work in Cavallari is gradient u squared y to the 8th power. And that energy actually blows up. And you need to renormalize it. And the term you renormalize is the boundary of gradient f squared and divide by 1 over epsilon. There's a cancellation going on. And that's the energy term where you capture the boundary behavior of this operation. So now, so this is in the flat setting. Now a question is, in this flat setting, we know there is this easy coordinate, Laplace A and Laplace B, where we can write down this operator. What happened on this general conformally compact curved manifold? And it turns out that, fortunately, Jeffrey Case, my co-author, has done work in this field before. So what happens is one should introduce other notion and rewrite the equation. So the other notion is the following notion. So on this manifold X, we begin to talk about warp product. Okay? So we warp it with product it with a conformal factor e to the minus phi f to the m. F is a manifold of dimension m. Now m sometimes is an integer, sometimes is a fractional number. So, and then we consider this metric. On F and H, we consider this metric, and then we look at its curvature. And we look at the P2K operator, this GJMS operator defined on this warp space. And then we restrict to X. Okay? So that's the so we have this operator defined on this space. And what is the nice choice of this space F given an X? Okay? And it turns out, and what are the natural weight M which one should choose? And it turns out it's the following. Okay. And so this is a notion. When M is infinity, then the Ricci curvature is the Barker-Emery-Ricci. Okay? And in this analysis, the Laplace operator, in this thing, the Laplace operator usually is expressed as Laplace phi is replaced by Laplace phi. So in the analysis, in this space, Laplace phi is Laplace minus gradient phi dot with gradient. So whenever one see operator Laplace, one replace it by this potential one. And our observation is the following. If we look at this operator, the Poisson operator, and then if we use this, we are saying that this operator, this solution, is equivalent to say, in our new notation, is equivalent to say that this, in this Yamabe operator, but with respect to its weight, is U is equal to 0. So this is the Yamabe operator, conformal Laplace, but weighted. And what is the suitable weight? The weight turns out is M, in this case, is 1 minus 2 gamma. And this phi now is e to the minus phi is equal to rho to the n power. Okay. So with this weight, then this is the conformal Laplace operator. And so, and then this helps us to understand what is going on in the extension theorem. Okay. So the first thing is, if we look at this second order PDE, we rewrite it using this weighted space P2U equal to 0. And after we rewrite that, of course, we understand that this second order PDE, U satisfy this second order PDE, naturally satisfy a fourth order PDE, because this is just multiplying this Chang operator by shifting the index S to S minus 2. Okay, so there is this is a minus. There should be a difference, S minus 2, N minus S minus 2, U equal to 0. And then we look at, so this S imply double S, and that is the Chang operator composite, the operator shifted by 2, composite U equal to 0. But this Chang operator can also be expressed, this Chang operator now can be expressed into in a Chang notion can be expressed in terms of this fourth order PDE P4 with weight. So this is P4, this S prime is equivalent to this fourth order Penny's operator now with weight. And now the weight shift. The weight now M2 is 3 minus 2 gamma, and e to the minus phi 2 now is equal to rho to the M2 power. Okay? So using this notation, everything is reduced to some operator, some form, which we are we know quite well. Okay. Now, using this notion now, it's like the flat case, we have an extension theorem. Okay? So the extension theorem is in terms of, it's like this corresponding in a flat case, it's like Laplace B squared equal to 0 in the flat case. And so we have an energy extension theorem. And now, the third thing is, in that case, in this expression of P4, phi 2, M2, there are many terms. There is this Ricci term, and then there is a Q curvature term, and so on. So what is the nice choice of the coordinate so that this equation gives us information and tells us so that its energy term is positive? And turns out that, again, this choice of rho star is a nice choice. This rho star, through this, we have this global choice using the Poisson function at the point 1. And in this case, our boundary scalar curvature is positive, so this is well defined. And we use the same metric, and then we see that it satisfies a lot of good PDE, and it has the following property. First, this scalar curvature with respect to phi m is equal to 0. That corresponds to my original observation is E rho star A equal to 0. Okay? So the scalar curvature correspond to it is equal to 0.
So that's a red product.
What?
That's a red product.
Yeah, but with weight, M1, phi 1, M1 is 1 minus 2 gamma, M2 is e to the minus phi is this rho star to this power. Yeah, the scalar curvature of the red product. Okay. And then when gamma is between 2 and 1, this turns out that if we shift our weight, M2 is 3 minus 2 gamma. M2 is 3 minus 2 gamma. I'm sorry, I have so many typos. And then this Q4 is equal to 0. Okay, Q4 is equal to 0. And then one can also compute the scalar curvature of the metric. Scalar curvature of the metric, restrict to the boundary, and find out is the same as the scalar curvature of the boundary metric and subject to a positive constant. But that constant is only positive when gamma is bigger than 1. So this argument only works for gamma bigger than 1. And then there's another critical condition. Another critical condition is we want to say that in this case, our interior metric is also equal to, has scalar curvature equal to 0, positive. Okay. So the philosophy is this Q4 is a fourth order notion. This says Laplace V2 of the scalar curvature equal to some curvature minus the traceless receipt of the curvature square. Because Q equal to 0. Okay? But this itself is not enough information. You need some second order condition to help you understand this PDE. And this second order condition turns out to be given by the boundary metric has positive scalar curvature. So what we want to say is for this nice choice of rho star for G star metric, this scalar curvature is also positive. For G star is positive. And the reason for that turns out to be here is a proof. So the proof of that is the following. It turns out that this S parameter, at this moment, we have n over 2 is here, and then we have this S is equal to n over 2 plus gamma. And we are in the range S n over 2 plus 1 and be above. Okay, so this is above. But it turns out, so this is, we are looking at V equal to PS at the Poisson equation equal to 1. It turns out there is another very special index that's S equal to n plus 1. Okay. And at that moment, at that time, this V at this index, it turns out to be the conformal metric considered by Jack Lee. Okay. And in this case, when V at S equal to n plus 1, this operator So this is Vs. This corresponding metric happen to have the constant. This is Laplace of the scalar curvature equal to scalar curvature is C1 depending on S R squared and C2 of this Ricci S squared. And in this index, C1 of n plus 1 is 0. Okay, so this metric happen to have the thing Laplace R is negative. There is a traceless Ricci is negative. Okay, so this is negative at this particular index. So Jack Lee's observation is hints the metric when it's restricted to the boundary is positive. Laplace in R has a sign, means its interior is positive. So this is the Lie metric. So which is positive. And actually, at the index S equal to n, there is another metric which has been earlier studied by Pfefferman and Graham to compactify this conformal Einstein metric, and that's a Pfefferman-Graham metric when S equal to n. And now, this Jack Lie metric has scalar curvature positive, so we can run a continuity argument. Okay. We know that our sequence, our metric, sequence of this metric, GS star equal to this rho S squared and times G plus, this sequence of metric has scalar curvature on the boundary, is always positive, and it satisfies this fourth order PDE, so there is strong maximum principle. Once it reaches 0 at some, the boundary is not happen on the conformal infinity. If it happened to the boundary, Laplace in R forces R to be strictly positive. So we always have a strong RG positive. And this observation, this continuity argument allows us to finish the proof of the theorem. Okay. So we have some Q curvature term which is positive, and this scalar curvature positive plus Q4 term equal to 0 allow us to control the energy of this fourth order N's term, and that finishes the proof. I already run out of the time, but let me say that some discussion. Okay? And one of the reasons we are interested in this problem is really we would like to understand more the result of Chang and Guillemot. And what they say is that on CCE setting, if the Yamabe metric on the boundary is positive, Yamabe constant, then the first real scattering pole is less than n/2 minus 1. So let me not explain what is this scattering pole. But this statement turns out to see that if the boundary Yamabe constant is positive, then its P2 gamma operator is positive. It's equivalent to say that. Their theorem is equivalent to this statement. And this result turns out it generalizes some early work of Chang and Yao. Okay? So in the work of Chang and Yao, they consider this special setting when this X is hyperbolic quotient of group. Okay? And then they consider M to be this domain of discontinuity of this group and quotient this group. And the theorem is to say M is of positive scalar curvature, then the Hausdorff dimension of the limiting set is less than equal to n/2 minus 1. But through the work of Sullivan, Patterson, and Peter Perry, and so on, they identify this Hausdorff dimension of the limiting set of the group with the location of the scattering pole, the first real number of the scattering pole. So this result of Guillemot and Chang generalizes this result of Chang and Yao, partially generalizes it to arbitrary conformal compact Einstein manifold instead of the special group, special setting. So in view of this result, really the question which one is interested is if Q2 gamma positive does that, we already know that it implies P2 gamma positive. The thing is, does it imply P2 gamma point positive for all gamma point less than gamma? We are interested to see that question. And that question, if one play with it, turns out to be related to the semi-group property of this class of the pseudo-differential operator. And in a flat setting, this class of this operator satisfies this composition property. And we know that on the standard case of the sphere manifold hyperbolic boundary, it satisfies P2 gamma 1 composite with P2 gamma 2 is less than equal to P of 2 gamma 1 plus gamma 2. So it's interesting to see if there are conditions on scalar curvature condition on the boundary so that the scattering operator has some semi-group property. We haven't got very far on the problem. And then I would say that the real question in this subject is there a real understanding this Q2 gamma is a non-local, or P2 gamma is a non-local operator, so this curvature, is there a geometric integration of it? At this moment, we only know when gamma equal to 1/2, this Q curvature is the mean curvature. And we very much like to understand what is the Q curvature. Okay, sure. Thank you.
I'm overwhelmed. Yeah.
So this fractional Q curvature or the fractional Pennet's operators for gamma non-integers, then these are not local operators, they're not differential operators. They actually depend on the entire local structure of the compact manifold.
Yes.
So is there enough pseudo-locality that you can hope that there's any way it reflects local geometry?
Only on this Rn, one knows you write it down, and it's a pseudo-differential operator is Ritz transform and with suitable weight. And actually, in the school of this Cavarelli and so on, they did place a notion called non-local mean curvature. But it's not clear if that notion is related to this.
But at least you do get some global invariance of a manifold that can be defined in terms of these operators. So
yes.
You've been asking about, you can play various.
Yeah. In some special setting, say 3+1 setting, and for example, we know what's Q3. Q3 is just in the Gauss-Bonnet formula for 3 manifold with boundary, there's this boundary term. And modulo this pointwise conformal invariant part, that's at the other part. That's Q3. So it does have geometric meaning in some special cases. Yeah. But in general, we don't know. So, yeah.
Any other question?
You mentioned the Schwarzschild metric as an example where you might apply it.
Yes, yeah.
But as an inner boundary?
You can write down it, you can compute, there's a way to write down what is the choice of this geodesic function and rewrite it, not using the original way of writing.
Okay.
Yeah, but you can redefine, find this geodesic defining function so that it's written in that. Yeah. Xinjie has done some work in that direction.
I was curious about C1 and C2.
Okay.
What's C1 and C2 combinatorial number?
These are numbers.
C1 and C2.
Yeah, these are, because I'm sorry, I have so many notations. This is my S, and then I use this S. So everything is with respect to S parameter. So that is a constant S. Okay.
The constant is some combinatorial number, right?
Yes, some number one can write down.
Yeah, okay.
Yeah. And then there is this S minus M plus 1 there, or something like that.
When S is an integer, this is a rational problem.
It's an integer. What do you, I haven't looked at it.
Maybe it's some.
Oh, yes. You are asking when S equal to N, in that case, this Poisson equation, you need to take its residue. So you need, instead of looking at the equation, you need to differentiate it with respect to S and take S equal to N. So at the integer point, there's a jump at those points.
Any more questions?
Is there any reason that any bakery Ricci curvature constitutes a positive?
At this moment, it's a notation for us. In this notation, everything looks natural. But in some sense, we are looking in that direction. We know the problem we are looking at. For example, Cavallari's problem, his computation is pretend you are looking at n plus 1 plus a space. So we know that you are adding a dimension, a extra dimension, and look at its Green's function, look at its property. So that leads us to think we need to add a space, and that space should be of dimension, the weight. And this notion happen to fit our need. Sure.
We thank the speaker again.